Hello there, Mr. Sutton here, bringing you the Algebra 2 9-5 homework solutions on making inferences from sample surveys. For this problem, the number of text messages sent and received in one day by a random sample of 30 teen cell phone users is shown in this table. We want to estimate the population mean based off of this. So to estimate the population mean, we're going to find the mean of the sample, which again we call that x bar, just to symbolize it. So basically we just need to take the average of all these text messages and that'll give us the population mean approximation. So let me plug all these into Desmos. I'll just do that off camera because there's a lot of them. So if we plug all of those in and add them up, it comes out to 1,962. So just do that carefully. And how many of them are there? Well, we could count them, but they told us there's 30, so we can just take them at their word. And now let's just do that division. So 1962 divided by 30, and that comes out to 65.4. So that is our estimation of the population mean, mu. On this question, they want us to use the data on text messages back in question 1, and then we want to estimate the population proportion row of teen cell phone users who send and receive more than 70 text messages a day. And then we want to do the same thing for those who receive fewer than 50 a day. So let's do the 70 first, part A here. We're just going to count the number of these that are more than 70. So go column by column here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Had a lot in that last column. So 13 that are more than 70. So that means we have 13 over 30. And then let's plug that in. So 13 divided by 30, that ends up being about 0.433. So that's our estimation of the population proportion for this particular measure. Now let's do the under 50s. So we've got 1, 2, 3, let's see, we got 4, 5, 6, 7, and that looks like that's it. So we have 7 of those, so 7 over the 30 total. And then again, let's plug that in our calculator. So instead of 13 over 30, we've got 7 over 30, which is 0.233. For this problem, we're going to do a little bit of civics work here. The President of the U.S., when they veto a bill, Congress, we know, can override that with a 2/3 majority vote in each house. 5 news organizations conduct individual random surveys of U.S. senators, and they're asked if they're going to override the veto. And the results are shown in this table here. So for the first part of this question, based on the results of the first 2 surveys, do we think the Senate's going to vote to override the veto? So in these first 2 surveys, we've got 85.7% and we've got 72.7%. That's above the 67% needed for that 2/3 majority. So based on the first 2, yes, since we're over 67% for both, it looks like we're going to get an override. Now the next question, based on the results in the table, so they mean all the results here, do we think the Senate will vote to override the veto? So the next survey that had a higher sample size than the first 2, we're at 75%, so that's still over the 2/3 that we need. But this is interesting. When we go up to the next 2 surveys with 31 and 49 for the sample size, I mean that's literally almost half of the Senate, now it's under 67%. So this seems to indicate, since we are under 67% for both of those with larger sample sizes, that means that probably no, we're not going to get an override on this one. For this problem, we have a national polling company claiming that 17% of U.S. public school teachers have a second job. You do a survey of a random 100 U.S. Public school teachers, and then you run a simulation of 100 random samples of size 100, around 17%, and this gives you the distribution below. So basically, if we had a 17% chance of getting someone to say yes to this question every single time, these are the different distribution, the different probabilities that we would have gotten each time out of 100. So we want to know what we can conclude about the accuracy of the 17% claim when 32 teachers in the survey have a second job. So let's find out the actual proportion based on the survey that we did, and then we'll claim it to the list of kind of expected proportions if the true value were actually 17% and we ran this with a random number generator. So 32 over 100, that's pretty easy to reduce. That's 0.32 if we make it a decimal to match the way this table is formatted here. And just sort of looking here, it's a little bit tough to read, but we've got, let's see here, 0.2, 0.3, 0.32 is all the way out here. There's no frequency out there. That's a frequency of 0. Since we have a frequency of 0, if this is actually the results that we got, then we would say, based on what we got, the claim of 17% is likely not accurate. Now, what if we instead got 14 teachers? So 14 over 100, that would be 0.14. And let's see, let's look at our distribution. Here's 0.1. Here is 0.11, 0.12, 0.13, and 0.14 is right before this little hash mark here. It has a frequency of 1. So on the face of it, that doesn't look very promising. However, we have to kind of look at the surroundings too. This is surrounded by some pretty high frequency things, and it's kind of right in the middle almost of this whole distribution. So because we're surrounded by high frequencies, we can say that the claim is likely accurate. This is definitely a value that we could expect if 17% were actually the true value. For this last part of the question, which we will call part B and fix our little typo there, we assume that the true population proportion is 0.17, so 17%. Based on that, we want to estimate the variation among sample proportions for samples of size 100. So we already ran a simulation on the assumption that 0.17 was the true proportion. So we just have to look at our simulation and figure out where the middle 95% of the results are between what percentage values here. So because we have 100 of these that we ran, that means we are going to exclude the outer 5. So, I mean, we can't really exclude 2.5 results on each side. So we'll just exclude 3 on one side and 2 on the other, and it'll have to be good enough. So let's see, we've got 1, 2, and half of these is another 1. There's 3 that I'm going to exclude on the left side, and I'll just exclude 2 on the right side. So one of them is this outer value of 3, actually this is 2.6. And I'll also exclude one of these 2.5s as well. I'm allowed to do that. So that means that our middle 95% is clustered between, this is still a 1.1 right here, and a 2.5. So between, actually not 1.1, this is exactly 1.0 right here. So between 1.0 and 0.25, that's what our variation should be if 0.17 is the true proportion. On this question, they're telling us that a distribution of data with a population proportion of 0.54 has a standard deviation of 0.06. We want to find and interpret the margin of error based off this. So since they're giving us the standard deviation, this is actually pretty easy. We just have to double the standard deviation, and that will be the margin of error that we're expecting. So 2 times 0.06, that'll give us 0.12. So that's our margin of error. Now what this means is that 95% of our values should be within 0.12 of this 0.54. So 95% of the sample proportions will be within 0.12 of this, which means they will be, if you wanted a range here, this would be like 0.42 to 0.64, or 66 rather. On the next couple of problems, they want us to find the margin of error for a survey that has the given sample size and then round it to the nearest tenth of a percent. So this time around we have a sample size of 1,000. So we have our formula, plus or minus 1 over the square root of n. So plus or minus 1 over the square root of 1,000 then will be our margin of error. And we will probably want to use the calculator for that. So let me do 1 divided by SQRT, square root of 1,000, comes out to 0.032. So that would round off then to 3.2%, plus or minus that. For this problem, we want the margin of error for a survey with a sample size of 2024. So let's just do plus or minus 1 over the square root of the sample size. And then going to Desmos for that, we got 1 divided by square root of 2024 comes out to about 0.022. So then 2.2% plus or minus would be our margin of error for this one. For this problem, in a survey of 920 U.S. teens, 81% said that helping others who are in need will be very important to them as adults. They want us to give an interval that is likely to contain the exact percentage of all U.S. teens who believe this. So we first want to find the margin of error here based on the sample size. So our formula for that again is plus or minus 1 over the square root of n, where n is the sample size. So we have plus or minus 1 over 920. Let's go to Desmos and get a percent, and we'll round that to the nearest tenth. So we've got 1 divided by square root of 920. So that's 0.033 if we round it off. So 3.3% plus or minus. So we're going to take the original value here, 81%, and we're going to subtract and add 3.3 to get that, to get our range of most likely percentages. So we have 81 minus 3.3. That's going to be less than or equal to the exact percentage, which is less than or equal to 81 plus 3.3%. So over here, this is going to be, let me think, 81 minus 3 would be 78, minus another 0.3 would be 77.7%. And then on the upper bound for this exact value, we're going to have 84.3%. In a survey of 2,000 U.S. adults, apparently 70% said they would support a national policy requiring rooftop solar panels to be installed on all new homes. Well, the price of housing just went up, but maybe the price of energy will go down a bit if they do that. They want us to give an interval that is likely to contain the exact percent of U.S. adults who support this policy. So let's start by getting our margin of error for this survey. We have 2,000 U.S. adults, and the margin of error is plus or minus 1 over the square root of n, the sample size. So plus or minus 1 over the square root of 2,000. Let's find what that is on Desmos. So let's replace this value in here with 2,000. So we've got 0.022. So plus or minus 2.2% if we make it a percent so that we can interact with this 70% here. So that means that the true value is 95% likely to be between 70 minus 2.2 and 70 plus 2.2. So that's going to be 67.8% on the lower end, and on the upper end, 72.2%.